Welcome everyone, and thanks for joining us this evening. My name is Jeff Myers, and I'm the Director of Partners and Alliances for the Energy and Utilities Industry Business Unit here at AWS. I'm excited to be joined this evening by two of my colleagues, Amit Kumar from ExxonMobil and Eugenia Sorotokin from Baker Hughes. We're going to share with you our work together in the digital oil field space, and I'm hopeful that you'll enjoy what we have to talk about this evening. We've got a handful of topics to cover. The first, I'll set some context about hydrocarbons and hydrocarbon growth in the world and some of the challenges that are inherent in growing hydrocarbon production. Amit and Eugenia are going to share with us what we think of as a high-value, high-complexity business problem that exists in the oil field, where we've deployed digital technology, artificial intelligence, and machine learning to solve. They'll share with us some of the challenges and learnings that we've discovered along the way. And of course, we'll talk a bit about where we go from here and what the path forward is. I think it's always important to start with a bit of industry context. As global population and prosperity continues to grow around the world, the U.S. Energy Information Administration estimates that electricity demand will double by the year 2050. That's going to require all forms of energy and energy production to meet that growth in demand, including traditional hydrocarbon production. So as a part of achieving that energy demand growth, the expectation is also that hydrocarbon demand will grow by nearly 47% over that same time period. Now, for those of you that are in the industry, you'll appreciate the challenge that represents, because growing hydrocarbon production really faces two key obstacles. The first is that by just natural phenomenon, production from existing reservoirs declines over time. So in order to add to existing production, you not only have to replace the production that's declined, but find new barrels of oil, if you will, to grow production from there. And then secondly, drilling new wells is a very capital intensive and costly process. Some onshore wells cost upwards of $10 million a piece, and offshore wells could be over $100 million a piece from a growth perspective, or from a capital perspective. So together with Baker Hughes, AWS and Baker Hughes have joined together in a strategic collaboration agreement to focus on the application of digital technology to solving this hydrocarbon production problem. We often say to ourselves that the lowest cost barrel is the one that you've already found and the one that you've already drilled. So our first priority in solving for this production growth problem is to maximize the productivity of your existing assets. So we also do that in the context of hopefully doing so with a lower cost basis, both lower capital cost and lower operating expense. Things like labor, cost of maintenance, spare parts, equipment out in the field. So we look to minimize the cost of operation of existing assets. And of course, in today's world, when you think about doing so sustainably, lowering both the footprint of methane emissions as well as CO2 production in the field is paramount. And of course, we operate in the oil and gas industry. It would be incomplete if we didn't talk about the need to improve and enhance the safety of operations in the field. And we do so actually by reducing the number of trips that operators take out to the field to monitor and manage wells. So with that as background and context, I'd like to invite both Amit and Eugenia to the stage so they can share with us some of the challenges that we see and that we are addressing in ExxonMobil's unconventional operations in the Permian Basin. Amit?
Thank you, Jeff. So as Jeff said, I'm Amit Kumar. I work with ExxonMobil, particularly in the unconventional domain. So I would like to begin by introducing unconventional domain to all you guys. So what do I mean by unconventional? By unconventional, I particularly refer to the tight oil and gas reservoirs, which has very low permeability. And the permeability is typically so low, you got to resort to using two key technologies to produce from them economically. Number one would be drilling very long horizontal wells. And these days, we are drilling wells as long as 4 miles long. For reference, the Las Vegas Strip, I was looking at it yesterday, and it's like roughly 4 miles long. So you can imagine the feat of engineering it takes to drill a full 4-mile long well. So that's the first technology. The other important technology we need to make use of is known as hydraulic fracturing. So for hydraulic fracturing, you need to pump water at very high pressure so that it goes and fractures your rock. And then you have to pump sand so that it goes into the fracture and keeps the fracture open, so that you could continue producing hydrocarbons once the fracture job is complete. So all these technological revolutions have dramatically changed how and where we produce energy. So today, more than 10% of the oil produced in the world actually comes from unconventional oil and gas fields in the United States. So production in the United States was in steady decline in the early 2000s, but the revolution of long lateral drilling and hydraulic fracturing has dramatically changed that. And the production from production in US has increased 2.5 folds since 2010 to roughly 13 million barrels of oil a day, and 10 million of that actually comes from the unconventional oil and gas fields, as shown in the bottom chart. Now, coming closer to home, to ExxonMobil, we also have very aggressive growth targets in the Permian. For those who are not familiar, Permian Basin is an oil and gas rich sedimentary basin located in West Texas and southeastern part of New Mexico. And our target there is to increase production by 50% by the year 2027 to roughly 1 million barrels of oil a day. And very recently, in the last few months, we acquired another major operator in the Permian Basin known as Pioneer Natural Resources. And if we combine the growth targets after including them, our target is now approximately 2 million barrels of oil a day by 2027. If you take the projection for the entire upstream production coming from ExxonMobil, that's roughly 4 million barrels of oil a day. So that goes to show the importance the company is placing on the Permian operations as far as our upstream portfolio is concerned. So this is obviously a talk about technology, in particular digital technologies. So where do we think digital technologies can help us achieve our targets? Before I do that, I like to highlight two key facts about the operations in the unconventional domain. The first would be very large well count. So today in the unconventional domain, ExxonMobil operates more than 10,000 wells. If we compare that to our prized deep water asset in Guyana, the number of wells we have there is around 100. So there are 2 orders of magnitude more number of wells we need to operate in the unconventional field. The second fact is the large geographic extent. So if you focus on the Permian Basin, it's distributed, if you look at the total area, is approximately 85,000 square miles, and that's larger than the state of Florida. So all combined, it should be obvious to us that each and every well in the unconventional domain cannot get the same attention that a single well in Guyana, for example, can command. That's number one. The second thing is, if something breaks, for example, your well goes down, it's going to take some time before you could bring it back online. So if you look at all the operators working in the Permian Basin, you would always hear downtime percentage of the order of 10 to 20%. So imagine 1 out of every 5 barrels is deferred. That's a lot. And this is where I think technologies, and in particular digital technologies, can help a lot. The first would be to ensure all the wells are being operated at their optimal set point. So if it's a gas lift well, the gas injection rate is set to its optimal rate. If it's an ESP well, the ESP frequency is set to its optimal, and so on and so forth. And we need these to be done through an automated algorithm and not manually. And typically in our past experiences, we have seen whenever we have gone from a manual approach to an automated approach, we see uplifts of the order of 2 to 5%. The second place where it can help would be in downtime reduction. And in that case, we need the entire spectrum of analytics. We need solutions covering the entire spectrum of analytics, all the way from descriptive analytics, helping you find wells that have gone down, all the way to the other side, predictive and prescriptive analytics, which helps you identify wells which are at high risk of failing so that you could take preventive actions and increase its run life. So this talk will be focused more on the latter part. Okay, so with that, let me dive into the life of a production engineer, whose role indeed is to make sure all the wells are optimized and the downtime is reduced. So what could be holding them back? In this slide, I list some of the challenges they face, and I believe this is going to resonate with a lot of the folks who are in the audience. Number one would be disconnected system. So a production engineer typically has to jump through multiple systems to gather all the data they need to make their decision. And this could be a very time-consuming process. This bottleneck creates an inefficiency in decision making and certainly holds us back from realizing our goal of operating all our assets optimally. So that's number one. Second would be manual process, and the one I typically like to highlight is the surveillance approach. Unfortunately, there are still people who do surveillance by going through all the wells they are responsible for. And as I said, there are a huge number of wells in the unconventional operations, so they might be responsible for 1,000 wells. The ideal approach would be you let an automated algorithm go through the data of all the wells and identify 5-10 wells they should be focusing on. But unfortunately, we are still not there. The third part would be siloed decision. So production engineering is obviously the focus of ensuring that, hey, all our operations are optimized, but it's also a shared responsibility with facilities engineering as well as reservoir. And many times the decision that is being made is kind of a local optimal to that group, not a global optimal for ExxonMobil, so to speak, which is a missed opportunity in my view. The other thing I would like to highlight is that the life of a production engineer is really very busy. They're always in a firefighting mode with many urgent things to take care of. As such, they have very little time for strategic thinking, for example, running different scenarios which could optimize their production, which can be a very time-consuming process in itself. So unless we make all that easy, they're never going to do that. And the last thing I'll highlight would be on adoption and sustainability. It is very common in ExxonMobil for people to move every couple of years. While that is great from the point of view of the career of the person, it keeps your job interesting, evergreen. It does create a challenge of continuously onboarding new people, bringing them up the learning curve, while still ensuring that all the wells are continuously being optimized every day to the best of the abilities. Also, it also creates a challenge in ensuring that the best practices are sustained and passed along the generations. So these are some of the challenges we face, but this is not unique to ExxonMobil, and Baker has been talking to a lot of external operators, and I'll let Eugenia describe some of her findings in their conversations.
Awesome, thank you for that great setup. Hope everyone's doing well today. A little bit about Baker Hughes, for those of you who may not be familiar. We're a Fortune 500 energy technology company. A really critical part of our business is our production business, which is about a $4 billion a year business. We manufacture equipment, chemicals, we provide services and digital solution to customers like Exxon, really focused on, in our production organization, the upstream oil and gas domain. We set out a couple of years ago to really pinpoint the area in the market that we wanted to focus digital technology investment. We're very cognizant of the fact that the future of this industry is going to be much more system-led and digital-driven, and so it's really important for us as we think about our business to innovate and come up with different ways to provide value to customers. So in our initial market research, the production space became really apparent as a critical area for the industry and also an area where we had a lot of domain expertise around. So at that point in time, and it feels actually serendipitous to be back at reInvent a couple years later, we formed our strategic collaboration with Amazon Web Services to create technology and solutions for this space. As we really looked at why production works the way that it does and why it's not more automated and system driven already, it became clear that it's just a very, very complex space. So there's a couple of examples of just the different parameters listed on the screen of things that a production engineer, like Amit described, needs to deal with. So they might need to be looking at their artificial lift equipment data, and they might have chemicals data that's actually in separate systems, and their production data may be, accessible from a different place. And they are actually needing to stitch together all of these different parameters in an organized way to optimize their production. And so our vision for this really, and we ended up launching a commercial software product called Lucipa around this, our vision is to be able to orchestrate all of those complex parameters and then also enhance with pretty significantly complex model engines some of these pieces. So today we're going to be specifically talking about artificial lift or ESP optimization, and the reason behind that is that has been historically one of the highest value areas that customers have asked for. It's been where a lot of our market research has shown that there's interest in solving the problems. It's also very, very complex to solve, so we're pretty proud of what we've done in that space, but just bear in mind that production is a larger picture. So with that in mind, I'm going to hand it back to Amit, who's going to tell us a little bit more about ESPs and why they're important to Exxon.
All right, so let's talk about electrical submersible pump, or ESP in short. ESP is one of the key artificial lift methods employed in the Permian Basin and beyond. So what is an artificial lift method? So as Jeff said early on, when we bring a brand new well online, the reservoir pressure is very high, and it's so high that you could produce at very economic rates, at very high rates all the way to the surface. But over time, the reservoir pressure declines, and so does the hydrocarbon rates, production rate. And in order to continue producing at sufficiently high rates, the well now needs some kind of a help. And that is done through what we call as an artificial lift method. In the case of ESP, that means installing a pump downhole that helps pump the fluid to the surface, again at high rates. So what is the main issue that we face, again, in the unconventional domain as far as ESPs are concerned? The main thing I'll say is the run life of ESPs. So if I look at the average run life of ESPs across different operators, not just ExxonMobil, it's typically around a year. Now, if I compare that to run life of a ESP in a conventional domain, it can last as long as 10 years. So there is a wide disparity in the achievable run life in a conventional domain versus an unconventional domain. And why does that matter? So every time a ESP fails, you have to go and mobilize the rig, which costs the money. You have to buy new equipment or rent new equipment. Again, that's going to cost money. But equally importantly, all this while you're not producing from that well. So that incurs downtime. And when you add it up over all the wells that you might have, it adds up a very big number. And I'll show you some numbers towards the end. So the next question is, then how can we improve run life? And here I would argue, what can we do differently which we haven't done before? Here I would argue in favor of using a predictive maintenance model, which has been trained on historical data, and use that predictive maintenance model to improve our current operations. And I think the timing is right to do that for three main reasons. First of all, ExxonMobil has invested a lot of money and time and energy in developing and maintaining a very strong data foundation. So we put all the data be it from any source or any application, we replicate all of the data in the cloud near real time so that could be leveraged in any kind of models. Number two would be availability of high quality libraries, machine learning libraries in the open world. That include things like TensorFlow from Google or PyTorch from Meta and many more from scikit-learn, to name a few. So that we don't have to build all of these from scratch. So that really helps accelerate the development process. And last but not the least would be the availability of cheap, I would say, and high quality cloud computing, which allows us to process data at scale and train our models. But at this point of time, we had all the ingredients necessary for success. But at this point, we did have to make one critical decision. Should we build it ourselves or should we buy it from the market? And there is a third interesting possibility too. If there is no existing solution in the market, could we collaborate with a third party and build the solution with them and make it suitable for our own needs? So we early on, we did some simple proof of concepts internally, and we quickly realized this is a hard problem to solve, and it's going to take a very long time to get to a decent solution. So that was ruled out fairly quickly. We also talked to multiple vendors, including Baker Hughes, on their Lucipa model, and we found that their model was easily the most advanced among all the vendors. But at the same time, it was mostly trained on conventional wells. And as I mentioned earlier, the behavior in unconventional wells could be much different from what you typically see in the conventional domain. So in this case, we decided to work with Baker Hughes on their Lucipa model. And I feel like it's a win-win solution. We get to leverage their advanced models. On the other hand, they get access to all the data from unconventional wells from ExxonMobil. Okay, so this slide, I give a brief overview on how we are using Lucipa in driving our day-to-day business decisions on ESP wells. For starters, I will begin by saying that Lucipa uses an ensemble of models approach. It uses many different physics-based models. It uses many different machine learning models. And the insights from all these models are combined to provide insights into the health of the ESP and the potential recommended actions to improve their run life. The output from the model can be broadly categorized in two different groups, and Eugenia is going to talk more about in the next slide. But I'll just lay some groundwork on that. So the first critical type of output or category of output we get from Lucipa would be the identification of critical conditions or the contributing factors which can lead to adverse effect on the run life of the ESPs. This could include things like sand production, it could include things like scale formation, it could be corrosion, it could be grounding and whatnot. And the other critical part or output from the Lucipa model is the impact of these critical conditions on the remaining useful life of the ESP, which is, I think, a novel output. And we use the remaining useful life to prioritize our action. At any given time, we might have hundreds of wells with critical conditions present. Which one of them should we prioritize for action? With all else being equal, we will prioritize those wells for which the remaining useful life has declined most rapidly in the recent past and take some action on it to improve their run life. Now, what type of actions one could take? There are a variety of actions. Some are relatively simpler, which could include things like changing the settings of the PID controller, which is a relatively simple, but it could still get tricky to deal with gas interference as an example. Or it could be more invasive action like doing a casing flush to remove the sand so that your ESPs can work more reliably. So this is how we use Lucipa, and this is the perspective of an end user. And I'll let Eugenia describe how things work in the background to make all of this possible.
Awesome. So we talked a little bit about critical conditions. So to double click on what is really a critical condition, you can think of a critical condition as a way to understand if one of those undesirable actions can happen to the pump. So when we look at critical conditions, what's interesting is that we use both physics models as well as machine learning models together to calculate those. We have physics models because we are a manufacturer of ESPs. So as we were building the solution, one of the things that we realized is that we have had internally used physics models for the ESPs to do activities such as sizing a piece of equipment. And so that would happen if a customer were to come to us and, as a manufacturer, ask for a recommendation on the exact parameters of the equipment that's best suited for their well. And so we've enabled those physics models to play an important role in this calculation of critical conditions as well as remaining useful life, which I'll give some examples of in a second. We also have developed machine learning models, which mostly you can think of these as being built by us having SMEs who can understand the data that's coming off of this equipment and being used to understanding what is an indicator of a critical condition. And so we've actually leveraged a lot of our internal teams who have historically had roles such as ESP monitoring, right? So someone who we might have deployed to work with a customer to work in their surveillance teams for ESPs. Those team members now are involved in actually the data labeling and the creation of these models. So it's a really cool, I think, way to leverage some of our legacy, you might call it, domain expertise to build a new digital solution. An example of how a physics model might interact with one of the machine learning models would be if we are missing data that's coming off of the equipment, which happens sometimes in production. We actually can run information through our physics models to create some synthetic data that then is provided as an input into the machine learning models. We map all of the critical condition data, which on this example, it might be a little bit hard to see on the screen, but you can see that Lucippa's detected gas interference, which is the little green bars, and then it's also detected that there's solids, and along the top, it's saying that there is a potential for a broken shaft. And so that's an example of both descriptive models, which are saying, hey, we're detecting that these conditions are existing, as well as a predictive model that's saying, hey, this broken shaft may occur if you continue to run your equipment in this way. What Lucippa ultimately is doing here is giving a recommendation, which in this case was taken where you see kind of the pink line going vertically. And in this situation, the action was to modify the PID or operating mode of that piece of equipment. And you can think of it as changing some of the parameters of the computer that's actually controlling the variable speed drive downhole. A really important piece of someone actually taking this decision, because if you think about it, the concept of trusting data like this and recommendations from a system to take such a decision is not the typical way that a production engineer would work, is actually showing them this impact on remaining useful life, which we've built using an ensemble of models. And a cool way in which we use both the physics and machine learning models together there is if, for example, the machine learning model is detecting that there's a gas issue, we can actually run that through our physics models, where with the physics we can calculate, hey, that gas issue, what kind of effect is it going to have, for example, if we know that that's going to impact temperature on different components of that piece of equipment. That then helps with the remaining useful life model, because it's actually telling us, hey, these are the pieces of equipment that have a potential to break, and so that's a variable that goes into that. So it's pretty interesting to be able to stitch those things together, and like you can see on this example, the recommendation was taken, and you can see the remaining useful life go up, although I've semi-aggressively put the arrow in a very bold manner so you can kind of barely see it, but you kind of see it going up at the bottom, which is a really cool outcome. As we were building this, we've obviously learned a lot, so we wanted to share a couple of the learnings that we've had with you guys today. And I'll first speak to a couple of the challenges, and I'll go into a little bit more depth of how we've actually solved for those. So one of the challenges that we encounter, especially if you consider that we're trying to build something that is deployable to not one, but to many customers as a framework, is that there is a lot of different pieces of equipment out there. There's a lot of different data coming off of those pieces of equipment. And so not just across multiple customers, but even across different wells from one customer, you might be getting variable inputs into your models. Another challenge is that a lot of the machine learning models have been dependent on us having really well labeled data sets, and we only have so many people that we can deploy and repurpose to data labeling. And so it's been really important that we're able to do that activity a lot more effectively. So on this first one, we've had to invest a lot of times into really creating a more robust MLOps framework. So the first piece I talked about is data input. So when you think about the type of data that we really think about when we are processing and mapping which models are going to work well or not in a particular scenario, is one, asset data, which is information like, what is the geographic location of this, because not all reservoirs are created the same. They have different conditions, so different models are going to apply. What's the specific type of equipment? What, is it an ESP? What kind of ESP is it? So those are all one set of parameters that's going to make models either applicable or not to a specific use case. And then the other set of parameters is all of the actual, telemetry type of data that's coming off of that equipment. And so being able to map what's available to what models are actually going to work for this use case has been a really important part of us in our MLOps. The other thing that we've had to do is being able to continuously assess the performance of these models and deploy the right ones to the right customer interface. So we do that really through two ways. One is by using pre-labeled data sets, and the other one is by having our SMEs do a validation as part of this cycle to say, yep, this model is producing the expected results, and go publish it. And a third piece of complexity that we've had is we're in a very highly regulated industry. So something that was interesting to me that I didn't realize before working on this project is that the capability to actually have an audit trail of what models were published when, that someone might have used to create a decision that they've taken, is not something that's generically embedded into a framework. And so you can see in this kind of image, in the last step before something gets published to production, we're actually ensuring that we always tag exactly which models are deployed to which customer, so that if something were to occur and someone needed to go audit or retroactively look at what was the technology that was used behind the scenes to give a certain result, we actually have an audit trail of that, which you find probably in industries like ours, you might find in banking, but it's not very widespread. The next thing that has been really interesting is being able to upgrade our data labeling experience for our SMEs. So one of the things that this is maybe more of a cultural thing that we've found internally, is when we build this type of stuff, internal teams might get scared of, it sounds like you guys are automating us out of a job, what's going to happen? And what we found is actually our domain experts have been our biggest champions of building this type of technology. So we actually originally made the mistake of having, some outsourced contracted resources that are, engineers do a lot of the data labeling. What we very quickly realized is that those teams don't necessarily understand the squiggles on the chart that are coming off of our equipment downhole. And so we were very fortunate that we had a team and some good leadership of these 24/7 surveillance type of personnel that already, work within Baker Hughes and understand how to read the squiggly lines and how to detect when something goes wrong, because that's literally what they do every day. And so a big priority of ours has been, how do we continuously upgrade their experience and make them really productive to help us label at larger scale. So where we're at now is that we have a more semi-supervised labeling experience where, once again, maybe a little bit hard to see on the screen, but you can see these bars that are on the chart is actually a pre-labeling process that we've created. They're using statistical labeling algorithms that are actually kind of pre-detecting when it looks like an event has occurred, right? And then the SME is then looking into that and validating, and it's able to make them work a lot more effectively. And they've been about 10 times more productive since the beginning of the project as we've continued to make these enhancements. But this is really an area that I see us continuing to invest into so that we can create more models with our team. And it's really also been a really good way for us internally to get our domain teams connected more closely to our digital projects, which I think we're going to see more and more convergence of those teams working together to deliver solutions. It looks like we have some slides repeating in our presentation, so I'm going to flip through them. Oh. All right. So principles for success. So one of the, as we take a step back and we really think, and I'm going to next, don't worry, let Amit tell you a little bit about the results. But one of the things that we've really learned in this is this has been a really high complexity use case. So it's taken us some time to get it going and get it right, and actually to get the models right and get our MLOps pipelines stitched together in the right way to be able to deliver this at scale. But one of the things that we're really proud of is that we've prioritized something that we knew was a high value use case that maybe we didn't know exactly how to solve for. And so I think as you think about which technology projects to take on, don't shy away from the high value use cases. I think another really important learning for us has been to focus on progress over perfection. And when I say that, I think in a lot of technology projects, even internally for us, a lot of times we see, hey, we need to get the perfect data to get this to work, or our user experience isn't perfect, we can't put it in front of a customer yet. And so we've been very iterative in our approach here. And I think the last one is when we think about who we actually innovate and work with, I think who you partner with really matters. So from the beginning of this collaboration, we obviously chose to partner with AWS because we knew that they could bring a lot of technical expertise and components that could accelerate our build. We used a really innovative technology partner called EPAM, who helped us get some more technical expertise that we were lacking to actually deliver and build. And then of course we've innovated with a really exceptional operator who has challenged us but also been patient as we've worked through kinks. So with that, I'll let Amit talk a little bit about what type of results this kind of solution has brought.
Thank you for that. All right, so in this slide, I summarize some of the results that we have seen in the pilot so far. So we have focused the pilot on the Delaware part of the Permian Basin. Again, it's located on the western half of the Permian Basin. And there are approximately 80 wells in the pilot so far. But before I dive further into the results and success metric, I like to share my learnings as to what is needed to make a pilot, or for that matter, any project successful. In my mind, there are 4 key ingredients to that, and if you miss one of them, your project might end up failing. So there would be the right data, the right technology, the right platform, and the right people. Let me explain. So Exxon, as I said earlier, we have invested a lot in ensuring that we have a very strong data foundation and that the data is widely available. So in this case, that would be a check. The second would be having the right technology. By that I mean the brains working behind the scenes. What models are you using? How are they trained? Again, Lucipa with them brought very advanced collection of models. And on top of that, we trained them on ExxonMobil's data, so that became highly and broadly applicable to us. So that is also a check. The third important thing is having the right platform. So by now, it's fairly well understood, even if you have the best model in the world, if you don't deploy it right, don't deploy it in a user-friendly fashion, it will not get used and end up adding value. Credit to the Lucipa guys, they did a very large user research before building their platform. and they further enhanced it with feedback from our own end users. So again, from a UI UX perspective, that's a check. And the last piece is having the right people, identifying the right people who would consume the results and act on it. So in this case, we identified surveillance engineers based out of our Bangalore tech center called BTC, who kind of consume the results from the Lucipa platform on a daily basis, and then they work with the Permian operations team to act on them and end up adding business value. So that is also a check in this particular case. Overall, how did we define the success metric for this particular project? We stuck to a very simple definition, which was 10 times return on investment. So obviously, we pay a certain amount of money per well per month. The question we are asking, hey, are we seeing at least 10 times that in return? Are we creating at least 10 times that value? I'm happy to share that we are definitely seeing that, and even with a few months left in the pilot, we have kind of already satisfied that particular metric. But our North Star would be, are we able to increase the run life by, let's say, by a minimum of 10%? And if we are able to do that and apply it across our entire Permian operations, that can easily create up to 25 to 50 million in value per year. And I think we are well and truly on our way to achieving that as well. So that is as far as the pilot is concerned. Looking at the more broader picture, this would be like, what is ExxonMobil's vision to how we operate our fields? And proactive ESP maintenance is only one piece of the puzzle. The other important thing for us would be system optimization. So we have been optimizing single wells for a long time. I think now is the time to go to the next step and start doing a system optimization, as we call it, all the way from the sand phase to the sales point, including many, many wells, including the facilities with all the constraints and all the glory. So that's the next thing on our plate. And again, we are doing multiple pilots in that particular space, including with Lucipa. And depending on the outcome of the pilots, we obviously want to scale it, move out from the pilot phase and apply it at scale to our entire Permian operations. And as we go along the way, there will be need to add new scope. One I can think of right now is that most of our compression fleet in the Permian is going to go electric from natural gas in the very near future. So that will result in an explosion of need of electricity. How do we optimize for that? But ultimately, our end goal, in particular my end goal, would be to democratize insights through a smart digital platform. So even if we have a new production engineer first day on his or her job, they can rely on this smart system, which has a huge cache of knowledge, can make smart recommendations, and they could help them optimize their wells every day from day one. I think that will be a recipe of success in this ever-changing world. So that is our vision for operations in ExxonMobil. It seems that Baker also has very similar vision for the product, so I'll let Eugenia describe that.
So we kind of talked at the beginning that ESPs is one attribute within a much larger network or system that is production operations. So when we think about, what does production operations look like in the future, we really think about it as being system driven. So that means that instead of a lot of these manual activities that are being done by people today, systems are able to consolidate that and really create this recommendation driven approach of interfacing with the data. We also see that this capability of bringing together the different parameters and being able to manage the interdependencies of them is going to become more and more critical, and really what we're looking to tackle. So for example, if you are able to increase your production because you've accepted a bunch of LUCIPA recommendations and now you're getting increased production from all of your wells, but you have capacity issues from your fluid handling perspective, which means that the fluids that you're actually pumping out, you don't have enough capacity of where to put them, that's going to create a problem, and that's actually not going to optimize your production because it's going to create an issue for part of your team. And so we really are looking at how do we capture the various individual components and optimize them, and then on top of that, optimize this larger network. And so that's really what our vision is. We're really excited in the progress that we've made towards it. Definitely a little ways to go, but we feel really confident that this is going to deliver a lot of value for the industry. And with that, we are at time, or I guess we're actually ending a little bit early, but we wanted to thank you all for joining us and really invite everyone. We'll be hanging out here, would love to have some conversations. Curious if anyone else is facing similar challenges or building similar solutions. Please feel free to connect with us all on LinkedIn. One of my most favorite parts of reInvent is being able to create some of those new connections, whether it's ideation, sparring partner, or just learning from other teams. So thank you all for coming today, and we hope to chat with you.